All right, so we're going to try to get the last two examples done here. Um, Sorry I split this over so many sections. Just it's been hard to find a big chunk of time to do it without interruptions. So we want to find, they're going to say let A be the area under the graph. So A be the area under the graph of f of x equals 2x squared minus x plus 3 over interval 2 to 4. And they want us to show that the limit as n goes to infinity of Rn equals that A. Or sorry. They don't want us to show that. They want us to compute. So use this to compute A. Since we don't really have another way of knowing, because that's not a nice like triangle like the previous problem, we don't have any geometric way to really verify that the area is correct. So what we're going to do is just try to compute it by figuring out Rn, take the limit as n go to infinity, and then just kind of trust that since, last time we let n go to infinity, it converged to the correct area. So as we let n go to infinity of this right endpoint approximation, it should converge to the area under that curve. So we need Rn. So Rn will equal, it's delta x, sum of j equals 1 up to n, f of a plus j delta x. A in this problem is going to be 2. To get delta x is the interval length, which is 4 minus 2, divided by the n number of intervals we're going to use. So in this problem, I'm getting 2 over n is going to be our delta x. So we got 2 over n, sum of j equals 1 up to n, f of 2 plus j times delta x. Delta x is 2 over n. So now I need to plug that into my function. So to do that, I get all of this is going to plug in for the x here and the x there. And then we're going to have to simplify that out, and that's going to take a while to simplify, I think. So we'll substitute into that function. So we get 2 over n series of j equals 1 up to n. And then it'll be 2 times this stuff here squared. I'm going to switch the switch where the j is on it like that. So that's 2 times x squared minus that plus 3. Okay. So I need to FOIL this out, then distribute the 2 across it. I need to distribute the negative there. This will be 2 over n, sum of j equals 1 up to n. 2 times, let's see, if I FOIL that out, that would be 4 plus, let's see, 2 times 2 over n, that'd be 4 over n j plus a 4 over n j plus a 2 over n j times 2 over n j would be 4 over n squared j squared. That should be, if I FOILed that all out correctly, we get minus 2 over nj plus 3. So now I need to let this 2 distribute. Then I need to combine like terms. And then we'll simplify it down and let the limits go to infinity. So that's 8 plus 8 over n times j plus 8 over n times j plus 8 over n squared times j minus 2 over n times j plus 3. Okay, so I'm going to write the j, sorry, this was a j squared term here, so the 4 over n squared was also a j squared. So I'm going to push my j squared term up to the front. So I get 8 over n squared j squared. I'll get my j to the first power term next, so I have 8 of them, plus another 8, 16, take away 2, 16 take away 2 is 14 over n times j. Then 8 take away 2 is 6. 6 plus 3. 6 plus 3 is 9. So we get this expression here at the moment, I think. Okay, now we're going to use the linearity of, actually, hang on, I'm about out of space here, so let me do this real quick to get some more space to work on. Give it a second there, go back up here, paste it all, and oops. Sorry, let me paste it one more time here. There we go. Okay, so we were down here. So we're going to use linearity to break this up. So I'll be able to view this as the sum of j squared, because 8 over n squared is constant with respect to that. So I will have 8 over n squared sum of j equals 1 up to n of just j squared. Plus, whenever I bring this in here, the 14 over n is constant with respect to that. So what I'm using again is I'm using that I can break, where's linearity? I can break up across the individual series, and then any constant I can push out front of the series. So I'm using that where I'm breaking this up across the pluses, and then these constant terms, I'm pushing them out in front. I'm pushing them out in front of their series. So we get that of just j plus sum of j equals 1 up to n of 9. Okay, so let's see here. Trying to think of what's going to speed this up. So let's let the 2 over n distribute to everyone. So we get 16 over n cubed. This right here is a power sum. So I'm going to use its power sum representation to write out here. So this is the power sum for j squared, which the power sum for j squared is, it's this, but it's also n cubed over 3 plus n squared over 2 plus n over 6. I'm just going to paste it down here so when I write it in, I can make sure I write it in correctly. So we got n cubed over 3 plus n squared over 2 plus n over 6. Okay, so that is this distributed, and then that written as a power sum, plus the 2 over n is going to hit the 14 over n, which becomes the 28 over n squared. This is the power sum for just j itself. So if we go up and look at that power sum, that was the n squared over 2 plus n over 2. So we're going to use n squared over 2 plus n over 2 for that one. So that is n squared over 2 plus n over 2. And then we get plus 2 over n. And then this right here, this is 9. And you have sum of 9 from j equals 1 up to n, which is going to be 9 plus 9 plus 9 plus 9 n times. So this will be times 9n. Okay, so next, we're going to distribute this to these terms. We're going to distribute that to those terms. We're going to simplify that out. So this, let's see here. We got n cubed and n cubed. The n cubes cancel. We get a 16 over 3. For this, there's 3 n's down below, 2 up top. They cancel. 2 cancels into 16, leaves an 8 over n. This, there's 3 down below, 1 up top, so there'll be 2 down below. 6 and 16 share a common factor of 2. So it would be 8 over 3n squared downstairs. Add to it, the n squareds completely cancel. You get 28 cut in half. 28 cut in half is 14. Out here, one of the n's cancel. The second one is still downstairs. 2 cancels into 28 to give you 14 over n. And then out here, the n down here cancels with the n up there, and you just get plus 18. We could try to add stuff further together at this point, but I think this is L over n, and all these terms here that have the n or n squared down below, if I let the limit as n go to infinity, all those terms will go to 0. So at this point, I'm just going to take the limit as n goes to infinity of this whole expression. So that goes to 0, that'll go to 0, this will go to 0. So rather than trying to algebraically combine them together, I'm left with the limit as n goes to infinity is of the left endpoint approximation is 16 thirds plus 14 plus 18. So let me see what that actually totals up to. 16 thirds plus 14 plus 18 is 112 over 3. So that is the area under the curve of that function over interval 2 to 4 using the right endpoint approximation. I think I wrote left endpoint down here. Sorry, it's right endpoint approximation. Right endpoint approximation. We started out with the right endpoint approximation. We're doing it the whole time as right endpoint approximation. So this right here, limit as n goes to infinity of the right endpoint approximation is 112 over 3. Okay, so we're almost done. We just got one last example that we're going to do, and then we'll stop there. So what we want to do is we want to look at, for this final example, we're going to kind of paraphrase. We're going to look at f of x equals x squared, and we're going to look over the interval 0 up to b, and we want to find area under curve. Since the right endpoint approximation is the easiest, I'm going to use the right endpoint approximation, and then I'm going to eventually go through and take the limit as n goes to infinity and show that we get show what our area converges to. And since we don't know this right endpoint here is b, we're going to have to do stuff in terms of b, so our answer is going to have a value b in it. Let's see, a is 0 plus j delta x. Delta x is going to be b minus 0 divided by n, so delta x in this case is b over n. It's interval length divided by the number of intervals you're going to break it up into. Okay, the function here is x squared, so we get b over n, sum of j equals 1 up to n. We get b squared over n squared times j squared. B squared over n squared is a constant with respect to the j function, so I can push it out front. We get b cubed over n cubed. All of that times the sum of j equals 1 up to n of j squared. This right here is one of our power sums, so I'm going to be able to simplify it down in a minute. I'll get b cubed over n cubed times whatever the power sum gives us back. And that power sum gave us back was the one for squared. That gave us back n cubed over 3, n squared over 2, n over 6. So n cubed over 3, n squared over 2, n over 6. So n cubed over 3 plus n squared over 2 plus n over 6. So I'm going to let this distribute to all of those. The n cubes cancel. We get b cubed over 3 plus here I get b cubed over 2n because 2 of the 3 n's cancel. There's still a single one below. And then out here I get b cubed over 6n squared. This is my right endpoint approximation. So I take limit as x goes to infinity. This should tell me what the area is. That'll be limit as, wrote x, I meant n, so I want limit as n goes to infinity. So limit as n goes to infinity of b cubed over 3 plus b cubed over 2n plus b cubed over 6n squared. All these terms here with the n down below go to 0. As n goes to infinity, those terms trend to 0. We're left with the b cubed over 3. And so that would be an expression of our area under the curve. So that finishes up section 5.1. It's kind of a long section, so we'll call it quits there. It's good enough.